So what are we saying here with inductance? We are saying that a change of current in a certain loop induces a changing magnetic field generated by this loop. And this changing magnetic field is felt by other loops in the vicinity in the form of an electromotive force on these loops. Okay, so the electromotive force E2 felt in loop 2 from a change in current in the first loop here is just equal to minus d dt of the flux going through the second one, and the flux is just the inductance times the current. So this just becomes minus the inductance between 1 and 2 with the di1 dt, where now we've simplified notations to exploit the symmetry between the two loops, because the inductance is a symmetrical property of these two loops. M21 is equal to M12. Just by looking at the equation, you see that indeed it's just completely symmetrical in 1 and 2. And therefore, it's like one quantity characterizing the geometry of these two loops here. So changing current in 1 induces EMF in 2, and the proportionality coefficient between the time-dependent current in 1, the time derivative of the current in 1, and the EMF in 2 is just the inductance with a minus sign. Okay, so that's the idea. So you can just induce stuff in neighboring loops. Okay, there are a couple of examples in the notes of computing the inductance of certain solenoids and things. I invite you to have a look at those. I'm not going to do them in class for lack of time, but you can just look at them. They're originally from Griffiths, so you can find those things. And I think they're actually originally from Purcell Morin. Griffiths was Purcell's student, by the way. Question? About the what situation? Previous equation. Here. So so you mean in this equation defining the inductance, the R1, R2? Or? So here the R1 is the position on loop 1 as you are integrating on loop 1. R2 is the position on loop 2 as you are integrating on loop 2. So for example, here that would be the R2, and then you would at some point have this R1 here. And the R12 is just now the difference, the distance between these 2 points here. But you're integrating both of these things over the whole loop. Okay? Yeah, there it goes. Okay, so that's a statement about mutual inductance, one loop to the other. But the fun thing is that you might say, hey, hang on. This actually works even if I have just one loop. Because if I have a loop that has a time-dependent current creating a magnetic field, then this magnetic field changes the flux inside my loop, and therefore it induces an electric field in my loop. Okay? So this is indeed correct. There is a notion of induced EMF in yourself, which leads to the notion of self-inductance. Okay, so self-inductance. What that means is that the changing flux through a particular loop is related to the EMF inside this loop. So here, what we're going to say is that the flux through the loop is going to be given by a proportionality coefficient L that will carry the name of self-inductance. Okay, so it's really just absolutely the same concept. And what we're saying here is that if I'm actually changing the current inside my loop, then I'm inducing an EMF in that loop from that changing current, which is just, once again, the change in flux, but now it's the self-inductance that goes here. So this is just minus the self-inductance times the time derivative of the current. Okay, so you're driving a current, you're pushing a time-dependent current in your loop. You're creating a changing flux. This changing flux is actually pushing back against your changing current by creating kind of potential difference for you to work against here. Okay, and that's the self-inductance of this. Okay, so here maybe yeah, a couple of comments in here. So inductance, the units of this are called henries, and 1 Henry is volt-second per amp. But again, this is just stuff you can look up, or just do dimensional analysis on these things, and you'll see it. Okay, but maybe it's worthwhile spending 5 minutes discussing a specific example of self-inductance here, because you know, it's kind of important to understand what that is. So let's try to do this. So example. What we're going to consider is a toroidal coil. We'll just draw it in a second. Let me try to make a nice little drawing of it. Draw 2 little rectangles. So what am I meaning with this? Imagine that, well, maybe the second one isn't so great. I'll just do one here. I will imagine that I have a certain axis here. This distance is going to be distance A. This distance here is going to be distance B. And a toroid, you know, I take a shape and I rotate it all the way around. Okay, so this is like a donut going all the way around, if you see what I mean, right? So I take my square and I just do a big circle with it. It's a huge donut with this rectangular cross section. And I'll give it a height of h, like this. Okay, now imagine that this object is made of wire that is wound around it all around. Okay, so toroidal coil, so inner, let's just be precise, inner radius A, outer radius B, height h, okay, and we will put n turns of wire around it in total, and we will drive a current I through that wire. Okay, does everybody get this setup? First of all, geometry of the toroidal coil, that's clear. Take my rectangle and I just do it around, I get my donut. On my donut, I take wire, I do 1 turn, 2 turns, 3, 4, 5, all the way around until I reach big N. And then in that wire, I am putting current I. Okay? So, what can we say about this? Well, we can compute the magnetic field inside that thing. So, would you know how to do this? I have my toroid. What do I need to do? I assume that the thing is completely rotationally invariant, right? I can just like rotate my viewpoint and it's absolutely the same everywhere. So what does my magnetic field look like in that object? So So let's say my current goes like this, right? Yeah, so you agree that there's going to be, in this case here, a magnetic field going like this way inside. Okay. Well, right-hand rule, right? So my I is going pum, 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 pum like this. Now I'm doing right-hand rule. So I've got, so if the current is going this way, then the magnetic field is going to pop out as a page here. Okay. So, so if I use, you know, this as my, like phi hat coordinate, the circumferential coordinate like this, right? So how would I compute the magnetic field inside here as a first step? That is one way of doing it, which will require you to do annoying integrals, but which would be entirely correct. There's a simpler way, because I've used the keyword symmetry, very symmetrical situation. So, so B inside the coil is going to be some, in some direction, which is circumferential, right? So what are the other names you can think of? Ampere, yes, yes. You said that? Okay. And what do I do with ampere? I can take the curl of B and I do the integral form. So let me write the integral form immediately of Ampere's law. I'm going to choose a certain path. I'm going to do dl into B. And what is that going to give me? Mu 0 times I enclosed. Perfect. So how do I apply this to this now? Should I invite somebody to show me how to draw? Maybe I can draw it. Okay, so so from the geometry of the situation, we expect the B to be circumferential. So then it's natural to choose a path P, which is a circle at radius r. Okay. So if I do this, and let's say I put myself outside of the solenoid here, outside of the coil, what's my magnetic field? So let's say I want to compute my magnetic field here. I've got my great big circle here, and what that tells me is that the so this thing here. So on the left-hand side here, what I would get, that generic radius r is just 2 pi r times b at this r, because the dl is just along phi hat, b is along phi hat, so phi hat dot phi hat is 1. And I'm just integrating over the closed circle here of now circumference 2 pi r, the field here. But now let's say that I'm indeed in here. What's my I enclosed? Well, there's 0. There's nobody. So B is 0 outside the coil, right? And if I am inside the coil, then you see, maybe we can try to draw it, right? So if I'm inside the coil, then my path of integration follows this here, right? So I'm doing this and then coming back like this. But now this path here defines a surface that is pierced by these current lines coming through. And I have big N turns of my current piercing through that surface if my circle is inside the coil. Okay. So here, mu 0 I enclosed is equal to 0 for being outside. But if I'm inside, then it's just n times I, right? Mu 0 times n times I, right? Everybody sees it? The blue circle here defines a circular surface. This circular surface on the inside bit here is pierced n times by the wire carrying current I. Therefore, the total current enclosed in that thing is n times I. You see it? Is that clear for everybody? Okay. Yeah? Hesitation? I'm not going to bite you. Yeah? Important you're able to do this kind of thing. Okay? So what does that tell us? What it tells us is that this B of R, you see, so B is equal to now, so I equate these two things. So I've just got my my mu 0 n times I divided by 2 pi r in the circumferential direction inside, and then 0 outside. Right? And you remember the kind of magical thing about this as well. If I was to use a completely irregular shape here for my cross section, the very same conclusion would be had. The size of the magnetic field is given by this simple formula here, irrespective of the shape of the cross section that you have here. The only requirement is that you have a toroid, namely that there's complete rotational invariance of your configuration. Okay, so that's one of the nice things about that. Okay, so that's the thing. But now, so our task was to compute. Well, we've got the magnetic field now coming from that thing with a certain current in there. So so we can now compute the flux through one of the turns. Okay, so now I'm going to take one of the turns of the loop like this, and I'm going to compute the flux going through now that surface. So if I'm looking at that little rectangle here, I'm now considering that as my surface, and I'm computing the magnetic flux through that. So what do I do? Well, I'm just going to have to integrate over this surface here the normal vector, which is just in this case the phi hat, but then with the integral between these limits of a and b radially and 0 and h on the this z-axis here. Okay, so really, if I have if I call this like loop 1 here, so the integral over the surface 1 here, dA dot b. So b is just that thing here. So I've got mu 0 n times I, and then I've got the 2 pi. So the integral over the vertical axis, that just gives me height h associated to it. But now the only non-trivial integral is the integral from a to b dr, because I've got this 1 over r dependence in here. So it's dr of 1 over r. So that just gives me a logarithm, right? Yeah, so mu 0 n I h over 2 pi with the log of b over a. Okay, so that's the flux going through one of the loops. But now I want to know the flux through all the loops but then it's just the same. I just need to multiply this by n. Okay, and now if I look at my equation, my equation tells me that the self-inductance is the ratio of the total flux divided by the current. So what that tells me, so this big phi is equal to Li. We've just computed phi, so we can just write that the self-inductance of that loop, L, is just mu 0 n squared h over 2 pi log of b over a. Okay, so I mean, the precise value of that thing is not important, but the physics of it is important. I have my big toroidal coil. If I want to put some current in there, I have to fight against the tendency of the coil to push back against what I'm trying to do. And this pushback is quantified by the self-inductance L. Okay, and now that you have that, you see if you're trying to increase the current, you'll generate flux that will work against you trying to increase the current. So you have to do work. And then temporarily you're kind of pushing this up until you reach the current that you want to obtain. But the calculation of this resistance to change that is manifested by this inductance, or in this case, the self-inductance, requires you to compute things very much according to things we've done before, computing the magnetic field for these configurations, and so that's a way to do it. And this is like not the simplest example, but I think it kind of contains many of the characteristics that you have here. So the first important thing to understand is that there is a resistance to change, and here resistance and inductance to change. Okay, something pushing back against you if you're trying to increase the current in this loop. And the quantity of this is the inductance. We've just seen the relationship between indeed the magnetic flux and the inductance in this. And that's how you